if you add noise to every single training sample and you corrupt 70% of the digits, it gets 100% accuracy. Transformer models are so robust that you can inject that much noise and still get 100% performance.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I am your host, Sam Charrington, and today I'm excited to be here with Alex Havrilla. Alex is a PhD student at Georgia Tech. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Alex, welcome to the podcast.
Thanks for having me. I'm excited to be here.
I'm excited to dig into our conversation as well. We're going to be talking about your research, which centers around the idea of applying reinforcement learning to reasoning and some of the downstream problems you ran into in the process. But before we dive into your specific research, why don't you introduce yourself a little bit to our audience, share how you came to work in the field, and we'll start there.
Yeah, so like you mentioned, I am a third-year PhD student at Georgia Tech. Technically, I'm in the mathematics department. My advisor does neural network learning theory. But 2 years ago, I got into open source LLM research through the open source community. And since then, have been very interested in RL fine-tuning for LLMs, and specifically with a focus on trying to improve their reasoning capability.
Tell us a little bit about how you think about your research broadly.
Broadly speaking, I am kind of dividing my attention into roughly two parts. So the first part is working on this more theoretical aspect, like I mentioned. So neural network learning theory, trying to, say theoretical statements about, given a certain number of training examples, how quickly can your model attain some minimum generalization error, how large your networks need to be in theory to, approximate some target function. And then on the more applied LLM side, my research is kind of a little more broad. I focused on RL fine-tuning. I was responsible with some other very talented people for the development of the TRLX library for open source RLHF. And that allowed us to do large-scale LLM RL fine-tuning experiments for RLHF, which kind of paved the way for doing large-scale experiments with reasoning, which was always my original motivation.
And when you talk about and think about RL for reasoning, how much of that is RLHF versus the more broad application of RL-related methods to improving the reasoning capabilities of language models?
There's no human feedback, so this is entirely automated. You can get whatever signals you're interested in from some ground truth label. So maybe it's very distant human supervision, but in the training loop, there's no supervision. But certainly, I think human feedback is also a very valuable way of, improving LLM reasoning with RL. So one great example of that is this OpenAI Let's Verify step-by-step paper, which trains this process-based reward model to give very granular step-level feedback to LLM solving math problems.
Lingering on RLHF for a moment, when you think about that as kind of the composition of RL and HF, you often think that we get wrapped up in RL and really the heavy lifting is done by the HF. Do you agree, disagree? How do you think about it?
So I think it's for sure true that the majority of the improvements that you see in today's LLMs are due to the human feedback parts. I mean, I think that was evident even if you look as far back as the InstructGPT paper. They had these comparisons where they have this kind of intermediate model, which they called the feed me model. This is TextDaVinci 2. And that model was already miles better than GPT-3. I mean, it was just much, much better. And then once you do the RLHF on top of that, the whole PPO pipeline thing, it improved somewhat. There was a 10% preference win rate improvement over that, feed me SFT baseline. But this is, nothing compared to the improvement you saw over the original base model. So I think, yeah, it's definitely true that the human feedback part is doing a lot of the thing. But on the other hand, I think the hope that many people have for RL, myself included, is that, if we really want to, start training these superhuman level systems, the amount that we're going to be able to provide high quality supervision is just going to naturally decrease as the complexity of the tasks we attempt to solve with these systems gets bigger and bigger.
Continuing along the RL vector, one of the historical challenges with reinforcement learning is its data inefficiency. Do you see us solving that by leveraging kind of unique properties of language models to make RL more data efficient and useful in this particular context? Or is it more about tracking improvement in general RL research and kind of pulling that into application with language models.
So like you said, more classical RL, yeah, extremely sample inefficient. Like you might have to wait around for like, hundreds of thousands of rollouts before you see like any emergent behavior at all, before your agent learns anything. Not the case with RL for LLMs. So like when you start, fine tuning these pre-trained LLMs, they start reliably improving like basically immediately. And this is, I think, because of like, there are a couple differences here, but the main difference is, like when you're fine tuning this LLM, you're starting, either from some supervised fine tune checkpoint or from, some like pre-trained checkpoint, which already has a pretty good sense of what it's trying to do, right? So like there's a very strong like warm starting bias, which you don't have in classical RL. And that was like really good for sample efficiency because you don't have to wait around for the model to kind of like, make random moves and then see if those random moves are useful. You can just, immediately start generating in the context of reasoning, you can immediately start generating potential candidate solutions, some percentage of which will be correct. And, you can get a pretty good reward signal from that immediately. And so that means sample efficiency is pretty good too. Like actually, in most of the experiments we did, we didn't require more than 100,000 samples most of the time to like, really fully converge to the max performance that we see.
Yeah, maybe with that in mind, kind of frame out, where we are with RL applied to LLMs. What are you're applying it to reasoning? Are there other ways that RL is promising in the application to LLMs? And kind of where are we, broadly speaking?
Yeah, so of course there's RLHF, like we talked about, super useful for, aligning the interactability of the model with how humans expect to interact with it. So there's that. I think also there's a lot of, work going to be being done and will continue to be done integrating LLMs with, various tool usage and allowing them to, act as web agents, for example, browsing on the internet, these kinds of things. And there will definitely be, RL components there. Which like, because that's a very interactive process, right? Like when you're learning a new tool for the first time, you have to figure out what are the scenarios in which should I use this tool? What are like, the preconditions for using this tool? And, anytime you have an interactive process that is very naturally RL focused.
Given the cost of like training large language models and their complexity, like is there an online component that RL makes possible for LLMs? How do we implement online learning in LLMs?
So first of all, online learning is still like a very difficult problem. So like this idea of, continual learning or like updating yourself as you go, still quite difficult. I mean, I think there are some naive solutions like, gather some data, fine tune the LLM on the data. And maybe those work okay, but it's kind of hacky, right? Like it's not really the solution we're looking for. But I think you bring up another good point, which is, and this is one of the main things we were investigating in the paper is these different paradigms of doing RL training. So like there's this online on-policy paradigm where you have some agent in an environment, right? And you're rolling out the agent and then you're training the like policy, you're updating the policy using the like data which has just been collected by the agent. So that's online and on policy. The agent's doing exploration and you're updating the agent using data which is generated. But there are kind of like more off-policy versions of this where you can generate lots of data and then the agent you're training and updating is like updated on a kind of old or stale data. So to like put concrete names behind this, proximal policy optimization, PPO, is an example of like a mostly online on-policy algorithm. And that's one of the algorithms we looked at in the paper. Expert iteration, you have a question and you sample the model many times on the question for many different solutions, and then you fine-tune the model on the correct solutions. That is much more off-policy because, you're generating lots of data and then you're, fine-tuning the model on like trajectories, which, may come from different points in like the training cycle. So like, and usually, like when you're doing this type of training in the classical RL setting, on policy algorithms such as PPO they're not more sample efficient technically, but like you need less iterations of like training to fully converge because you're exploring this complex state space and somehow the updates you make to the policy are like the most useful ones you're making in the context of solving the problem. And off policy is somehow like converges slower. in comparison in classical RL. But this is not at all what we found in when we were like comparing these methodologies in like RL fine tuning for LLMs. So when you look at the sample complexity or the number of samples you need to reach a certain level of performance for PPO versus expert iteration, it's roughly the same, to be honest, despite the fact that expert iteration is much more off policy and potentially generating less useful data. Which I think a priori is a bit of a surprise because this is, not the case at all in classical RL. So these two methods have roughly the same sample complexity. And like I mentioned before, like the overall sample complexity you need for these models to converge is like fairly, like pretty small, like only 100,000 samples. So like somehow this is an indication that like definitely the models, are learning something and are like uncovering interesting behavior, but somehow like, they're not really accessing, they're not somehow diversely exploring in the way that we might want them to. Because otherwise, if they were accessing, like new types of solutions and new modes of behavior, you probably wouldn't see such like fast convergence and like such similar sample complexities between these methods.
Let's maybe punch into the paper so that we can talk about some of the broad RL concepts and their applicability kind of more concretely. So the paper is, again, teaching large language models to reason with reinforcement learning. Talk a little bit about your motivations with the paper.
Yeah, so I already kind of touched on it, but in the RLHF space, there are many different algorithms now that are popular, right? So at the beginning, there's PPO and PPO with soda, and it was unclear whether you could use other algorithms. But now, on like April 2024, it's clear that, not only are there many competitors, but they're basically just as good, right? So there was a recent paper from Cohere, which shows you that reinforce is basically as good as PPO in this context. DPO is obviously very popular now and does no exploration at all. Which is also maybe another sign that something is not quite right here. But is, basically just as competitive as PPO, which does lots of exploration. But, when I was investigating these problems, this was not clear. Like, it was not clear, how do these algorithms compare? Like, what are the benefits of using one RL algorithm versus another for, doing this fine tuning? And so this was really our goal, like, we're going to take all these algorithms and we're going to take a bunch of different ideas in RL, and we're just going to see what works best when you're fine-tuning RL.
The context here, specifically human feedback or something else?
This was not RLHF. So in the context of reasoning, usually you have a question and then you have an answer. And that answer has like a goal final answer you're trying to reach. So like, maybe it's some math word problem and you're trying to get some integer solution to the math word problem. And then, we can give a reward in the most basic sense. We can provide a reward feedback based on, did you get this correct final answer or did you not? And that's how you can start to do the RL.
What's the relationship between the policy and the language model itself?
Okay, that's another good question. So in this case, the policy is exactly the language model. So the language model generates every single action and then, is supposed to come to the correct final answer. But I think this is a good question because there are situations in which, the policy is not necessarily just the model. So, for example, you can imagine combining a calculator with an LLM to solve math problems. We didn't have to do it here because we were working with Llama 2 based models, and Llama is pretty good at arithmetic, or at least the types of arithmetic we were doing. So there was no need for a calculator. But you could imagine combining a basic tool like a calculator with the LLM, and that forms, like a more generalized policy, which is the combination of an LLM and some tool. So yeah, just to kind of drive home the point that the policy doesn't necessarily have to be the LLM.
If the policy is the language model, what does it mean to optimize the language model? Are you optimizing, or what are your levers? Are they like things like temperature and things that go into a prompt? I'm imagining that they're not the model itself.
In our case, it is the model. So like we are literally like changing the weights of the model depending on, the type of reward that, he is getting back. Like, did you get this question correct? If yes, like change your gradients in a way to, adjust for this. If you got it wrong, okay, maybe change your gradients in a different way.
Got it. Yeah, I was imagining that the model was embedded in some larger system and you were tweaking something about the larger system as opposed to the model itself.
I see. Yeah, we're directly fine-tuning the model.
Got it. And so you alluded to one of the big results that you saw that the algorithms all performed largely the same. Is there a next level of nuance or detail there?
Yeah, I think so. So let me expand on that. So we went in expecting, PPO to do quite well, like get the best performance and have pretty good sample efficiency. Because like I said, it's more on policy. It should be more, efficient in some sense. It should converge faster. But yeah, I mean, this is simply not what we saw. So, like I said, expert iteration, for example, where you simply fine tune on the correct answers, performs roughly the same. In our setup, technically, it was somewhat less sample efficient, but we did some ablations which demonstrate. Okay, so to be very concrete, the way we implemented expert iteration is, we sampled the model like 96 times per question or something, and then took all the answers which were correct and fine-tuned the model on those and iterated that. But then we did some ablations.
Correct in this case is determined by human feedback?
Right, yeah, because like for each answer, you have like a ground truth correct final answer, and that has been labeled by a human.
In the training loop, you're just, doing text comparison or something automated to make sure that the correct answer is there.
Exactly.
But you do have the correct answer because they're ultimately math. So it sounds like were they all simple arithmetic, or was that just one category of reasoning problems that you?
Yeah, they were mostly simple arithmetic. We also considered some like common sense question answering, but the majority of it was arithmetic, like GSM-8K style questions. But just to finish describing the setup very concretely. So like for expert iteration, we had like 96 samples per question, and then we fine-tuned on all the correct answers. But it turns out like 96 answers per question is kind of overkill. Like you can reduce that to 4 answers per question, get nearly the same performance as you had before, like after each iteration. And then you can match the sample complexity of PPO, and then you still beat PPO's performance. So yeah, and then we investigated some other setups as well. So we investigated in the offline case where you don't do any exploration. There's this idea of like conditional fine tuning where you can like label each step as like correct or incorrect using good or bad tokens. And so like we thought, why was this the case? Like why is everything performing roughly the same? Because we also tried some other ideas as well. So like there are these ideas of training reward models in the literature. So this idea of an outcome-based reward model where you can predict the correctness of the final answer. And like somehow this might, smooth the type of reward that the model is getting. Because like previously you only get a reward of +1 if you got the correct final answer, and you got a reward of 0 otherwise. But like maybe you're really close, but just slightly off in some way. So hopefully the reward model can tell you that. So we experimented with giving that as a reward, both like at the very last token, and also like kind of interspersed throughout. So it's this idea of a sparse reward versus a dense reward. And again, we found in both cases that these mechanisms improve the sample complexity of the learning algorithm. So like if I give you an ORM as for a sparse reward or a dense reward, you need slightly less samples to converge, but the peak performance to which you get to is about the same or slightly worse than if you just use, the ground truth exact match text match reward. And like, we were thinking, why is this the case? Like why is it that even when we give this, better reward, the algorithms all must roughly converge to the same thing? And so our main hypothesis was that, okay, if these algorithms, especially PPO and expert iteration, are all producing roughly the same data, if they're all producing roughly like the same exploration of the types of answers which constitute, like the types of answers which they discover in like the exploration process, that would, kind of explain this phenomena, right? Because, regardless of the algorithm, if I give you more or less the same data, then they're probably going to perform roughly the same in this context, at least. So to verify that, we, had to look at, some measures of, what is the like type of output that each of these methodologies or algorithms are producing. And in particular, we were interested in 2 metrics. So we were interested in looking at the diversity of the solutions which these algorithms, which each algorithm generated. So like, what is the unique number of solutions for a given problem where you judge two solutions the same if like they have the same order of operations or something like that, arithmetic operations. So that was one metric. We were looking at output diversity. And then we were also interested in, if you look at the pass at 96 metric, which of these like trained models, which is if I sample the model 96 times on each test question and then check if I ever get the same test, if I ever get the correct answer, that's another metric I can use to evaluate these models' performance. And that's also some measure of output diversity because, there's this, roughly speaking, the idea of a model being more diverse means that if you sample it many times, it'll have like a broader set, broader coverage of the types of solutions, and its odds of getting the correct solution are, better than the less diverse model. And so their pass at 96 score will be higher. So we were comparing the pass at 96 score of these models, and we found some very interesting things. So, for example, if you do supervised fine-tuning and you train for like 2 epochs on some like Golan ground truth data, your pass at 96 score will be pretty good. So like you can get a pass at 96 score of like 80% on Llama 2 7B if you do this. But then the interesting thing is, if you train for longer than that, so if you train for more than 2 epochs, your pass at 96 score will start to go down. And suddenly it seems like your model is producing less diverse solutions, and the exploration it's engaging in is worse. So like somehow supervised fine-tuning is not, like too much of it is damaging model diversity.
I'm not sure I'm clear on the role and value of diverse responses for simple arithmetic problems.
So I agree. Like if you're trying to solve a math word problem, on the face of it, like why do you care if you are able to solve it in like multiple ways, right? So first of all, I want to clarify that even in these simple math word problems, there are a surprisingly diverse number of ways to solve them. So like on average, I can tell you that the 7B model discovered like 5 different unique solutions per problem, which is kind of surprising, right? But like, already pretty diverse. So like, why is this useful? I'm making the claim, it depends on your use case. So like if you're interacting with ChatGPT, for example, and you're just asking ChatGPT, solve me this word problem, then I agree. You don't care about output diversity. You just only care about ChatGPT getting the right answer. And if it can do that reliably in the first try, that's great, okay? And so, yeah, you don't care. But, like, let's say you're interested in, like, maybe you have, like, some two different types of, like, difficulty of questions, right? So, like, you have an easy set of math problems and you have a hard set of math word problems. Maybe I can convince you that if you can generate lots of diverse types of solutions to the easy math word problems, somehow this makes it easier to also generalize to solving the harder math word problems.
A model with a greater agility with regard to reasoning can probably do better with the more complex problems. Whereas for the easier problems, it might be more like, memory or retrieval or something like that.
Yeah. The reason I think we care about this very concretely in the RL context is because the ability of the, agent that you're fine-tuning to produce diverse solutions directly impacts the quality of the exploration it's doing as it's being trained, right? Like if I have a LLM which is being fine-tuned with RL and it's like, super overfit, has no diversity, it's like just not going to be able to discover that much and like not going to be able to learn that much beyond like what it already knows, right? Because it's, simply not generating surprising or unexpected solutions. Whereas if you have an LLM which is not overfit and is able to, generate more diverse, interesting solutions, then you're going to start to see the more, complicated type of generalization that you're interested in.
What's the relationship between exploration and diversity of responses and temperature, which I mentioned earlier with LLMs?
Temperature definitely will have an effect on exploration and like model output diversity. In general, in our experiments, so it depends on the setup. We have 2 broad setups. One, we supervise fine-tune the model beforehand and then do RL. And the other, we fine-tune the model from the pre-chain checkpoint and then do RL. In the case of supervised fine-tuning setup, you can afford a slightly higher temperature of like 0.7 because the model already has a decent idea of what it has to do. When you start from scratch, you need to have a lower temperature of like 0.1, 0.2 because the model just doesn't have a good of sense of like, what actually constitutes a correct solution. It's still learning the syntax, that kind of thing. And so you can't really afford to be slightly off. You really need to like make the best of all like the valid examples you have. But what you can do is as you go through training and the scratch, like the starting from scratch case, you can start to anneal the temperature so that you're producing like higher temperature solutions as the model is, better learning what constitutes a valid solution.
Are you tuning just the last layer, or kind of how deep are you tuning and that kind of thing? They're all different things you could play with there. But they're not fully specified, I don't think, or didn't think, by the RL algorithm itself.
Yeah, I see. Yeah, I misunderstood. So yeah, from that sense, like what layers of the model are you fine tuning? That's all the same between different algorithms. Yeah. But like how you actually compute the gradients and like the loss which is used, that's algorithm specific.
What's the next big takeaway?
Yeah, so another interesting thing is, so I mentioned like this phenomena of, and this was observed in the original GSMAK paper actually, so I don't want to claim credit for it. But there was this phenomena where if you have a model which you're supervised fine tuning, if you do it for like 2 epochs, it has pretty good diversity, but then diversity pretty quickly decays after that. So like hopefully I've convinced you at this point that it's in your interest to maintain model diversity if you want good RL. So the nice thing that happens when you do any kind of RL fine tuning, PPO, expert iteration, anything really, is that pass at 96 parameter kind of maintains, like it converges pretty early in training, but at least it doesn't decay. So like maybe it converges to 80% and then it stays at 80% for the majority of RL, the RL training, versus in SFT it like it's this unimodal thing where it like increases and then decreases. So somehow like RL fine tuning is able to reinforce and preserve like the type of diversity that the model has like picked up on and started to learn. What you're really doing during RL fine tuning is you're expanding the kind of like this database of training data that you have, and just like training the model on more diverse data allows it to maintain more diverse outputs is what I think is really going on there. But that's kind of like one nice byproduct of the RL fine tuning, is that you maintain this level of diversity you wouldn't otherwise get with supervised fine tuning. There's this interesting literature in classical RL, which is autocurricula. So like if you have some agents on a bunch of different environments, some of the environments will be harder than other environments. And so you want to like, train.
Start them easy and increase the difficulty over time.
Yeah. That has worked pretty well for classical RL. So we tried a couple different algorithms like that in our case, with the LLM fine tuning. So to be concrete, we tried PLR, which is prioritized level replay, which is one algorithm. And we also tried this idea called backtracking, where you like start the LLM with like the answer to you start the LLM at like a solution which is almost done but not quite, and so the LLM only has to fill in like the last 1 or 2 steps, and then when the LLM demonstrates it can fill in that last 1 or 2 steps, it backs itself up slightly, and now it has to fill in like the last 3 steps. If it can do that, the last 4, etc. So you're kind of like backtracking to like early and earlier steps in the solution, and you can see that as like being easier than solving everything from scratch, right? So we tried these kind of ideas. And again, I mean, there were like maybe some small benefits, but they weren't, like really inducing the type of like generalization improvement that we were interested in. The model is kind of already going to, you're going to sample it and it's going to produce solutions in some specific way. And all of these algorithms that we tried are like not really doing a good job of like significantly changing the sampling distribution of the model. And so that's why the performances are roughly the same.
Kind of given what you learned in this research, if you were, working on Llama 3, for example, and wanted to ensure that it had, better reasoning capabilities, like, is there an obvious way that you would kind of integrate in the results of this research?
Yeah, so I think at my point, my opinion is exploration is the fundamental problem here. I think it's clear that there are a couple of things which clearly do work well at improving like the quality of model outputs. So if you somehow have really high quality data coming from another source, like humans, for example, or GPT-4, that clearly works very well. You can fine tune a model on those, and the type and like of solutions it will produce is like significantly changed by this. And I'm sure Meta's already doing this, right? Like, of course, they're getting humans to annotate high quality data. If you want to take the extra step, what you really want to do is you want to start looking into like comparing and benchmarking how different algorithms impact like the quality and diversity of like synthetic data that you're generating. So like people right now are very interested in synthetic data generation, but there isn't that much investigation yet into, how just the quality of the data generated by one algorithm compared to the quality generated by another algorithm. How does this compare as a function of fixed compute, fixed number of samples? Also, how is the diversity impacted? I think really you want to have a rigorous benchmark which tells you if I have these different ways of generating synthetic data, how do I get the best bang for my buck when I'm comparing some targets level of quality and diversity in the output.
You also have recently been involved in a benchmarking effort, a data set called ARB, Advanced Reasoning Benchmark. What's the relationship or contrast between that and GSM-8K, which you referred to?
Yeah, so ARB is just impossibly difficult. So difficult that certainly I would not be able to solve most of the questions without a reference solution. And this is really the direction most benchmarks are going nowadays because LLMs are, really just are so capable. You really a popular benchmark right now is graduates, it's GPQA, graduate something questions, which is similar to ARB. I think a bit different in the sense that one of the things we were really going for in ARB is we want really high quality, really difficult questions, but we also don't just want questions which have a numerical final answer, which you can check that way, right? So we certainly have those in the benchmark. So really difficult questions that you have to get to correct numerical final answer. But we also have some questions which investigate the ability of the model to do symbolic reasoning. So maybe the final answer is some polynomial or something, which you need to get to. A lot of more advanced math questions and physics questions are like this, where your final answer is not numerical, it's also symbolic. And, this is obviously an important type of question to be able to answer. Also proofs, we have a couple high-level proof questions in there that the model needs to be able to, solve and write a convincing proof for. GPT-4 is pretty good at doing arithmetic, right? I think a lot of people have remarked on this. If you ask it to multiply two 5-digit numbers, it probably will be able to. But then if you are asking GPT-4 to add two very simple numbers, asking it to add, 10 and 11 or something in the middle of a very long computation, it's integrating stuff and it's summing some power series. It's doing lots of complicated stuff. GPT-4 will tend to mess up very simple arithmetic operations, which it was completely fine and able to do in a clean context. Which is kind of funny, right? This happens to me all the time. I'm doing some hard math problem and very high level abstract stuff. But then when I actually have to go and simplify, I suddenly, freeze and I'm oh, wait, I'm making mistakes here and I have to go back and check my work. So somehow it's funny that GPT-4 exhibits this same, I would say, characteristic that humans do when they start to learn higher level mathematics, this kind of thing. I don't know why exactly that is. It might, in some way reflect just the difficulty of reasoning over long context. Actually, I'm sure it does. I'm sure that's part of it. But also, I wonder if it in some way reflects the training data itself. Maybe, the training data you have for these types of more long, complex questions is filled with arithmetic errors, this kind of thing, which you just don't detect because when you're looking at a graduate level question, you don't actually care too much about the arithmetic itself, right? You're more interested in the more complex, sophisticated reasoning.
Attention is obviously a super overloaded word, but it strikes me that there's maybe something in what it's paying attention to as it's what it is, how it's conceptualized the goal, from a distribution perspective of the output as it's generating the tokens, and it maybe gets distracted by the bigger picture and misses the smaller things or something like that.
It's distracted by, this integral and suddenly it can't add 6 and 5 or something like that.
you expect it to be a lot more consistent. If it knows how to add 6 and 5, it's going to know how to add 6
Right.
and 5.
Yeah, which is fascinating that it's not like that. So
how has it changed the way you think broadly about reasoning, machine reasoning, LLM reasoning, and the future of reasoning?
we didn't get to touch on noisy algorithmic chain of thought. If I'm teaching LLMs to do addition or like multiplication, like very simple algorithmic tasks, how does their performance depend on, like, if I start injecting, little tidbits of noise here and there? So like maybe I flip this digit from 5 to 7, or like I delete this line of the calculation.
It sounds a little bit like kind of the approaches that are often taken for like interpretability research. Like, let's fiddle with the input data, make it a little noisy, and see, how that changes things in the model.
We're specifically looking at like noise effects training for chain of thought. And like in preparation for this work, I spent a lot of time thinking about like, okay, why is chain of thought useful to begin with, right? Like, it's also clearly very useful to humans. Like humans, had spoken language for a long time before, like writing things down became useful. And like suddenly I think like it's clear that once humans started writing things down, this was a significant shift in like, the trajectory of the human race or whatever. I'm no authority on history, so this is just my take. But there's clearly like a huge power to writing things down. And I think like one way of interpreting it is it's like a way of maintaining state. Like if I am doing this long, complicated computation, I'm like adding up 2 7-digit numbers. I have to do all of that in my head, and I have to maintain the state in like individual neurons on my head, right? Whereas if I'm writing things down and doing step-by-step chain of thought reasoning, I'm able to offload most of that state onto the sheet of paper, right? And then I can just refer back to the sheet of paper for like, certain subsets of information that I need. And that's hugely useful. Like that just, simplifies significantly the type of computation that needs to be done neurally. Certainly for humans, and I think also for LLMs as well. Like it literally makes the next token prediction task much, much easier.
Chain of thought has proven to be useful, and based on chains of thought that have naturally emerged in the training data, but there's some way to maybe take advantage of or kind of design for the way LLMs might think about chain of thought and like train on more specific chains or something.
Getting LLMs to do like refinement and this kind of thing, right? Like, you have some solution and you try to fix the solution. And often when humans are doing refinement, like there's this whole intermediate thought process, right? Like you have some sequence of thoughts, you say, oh, there's an error here, you try something and that doesn't work, you try another thing. But that's not written down anywhere, right? So like oftentimes we get to the correct final answer, but we don't show our work. And so like a lot of that work doesn't show up in the LLM training data, but I think putting those intermediate steps in the LLM training data will be super helpful. I think that's, something probably pretty much everyone agrees on and most people are doing. Our key questions are, A, how do you characterize this type of noise in like chain of thought data? Like, are there different types of noise which impact the model differently during training? And then B, how can you quantitatively model the impact of these different levels of noise on like, trained model performance?
If you're training a, GPT-N, you might be able to profile some new data set that you have access to, characterize its noise, and then understand the impact that it's going to have on the model that's produced.
Yeah, that's exactly the idea.
Okay.
Like I think it's important to be able to identify these factors, right? And say like, yeah. So like now to like explain what we found. So we trained like a small model. This was a relatively small scale study. We trained a small model, Pythia, for 410 million parameters, and just like sequences of text produced by like simple functions on integers. So we did arithmetic. We did, if you have a list and you need to find the median in the list, we did that. We did sorting. We did a bunch of GCD, greatest common divisor. We did a bunch of different algorithms, which produced like chains of thought for. We call them algorithmic chains of thought because they're algorithms. And then we trained trained models on them. And first of all, like chain of thought makes the task much easier. Like if I am training even like, a small GPT-2 model to do arithmetic, it's much easier if you write out the chain of thought for the model versus training from scratch, like just going from like X plus Y to Z. That's much easier. So then once we confirmed that, we characterized different types of noise. So we came up with two different types mainly. So there's static noise, which is kind of noise which like maybe makes local changes to each chain of thought. So like maybe you flip a digit or maybe you delete a line, but that doesn't change anything like earlier or later in the chain of thought. It's just that specific line. But then we also have a kind of more pernicious, more dangerous type of noise called dynamic noise. And what dynamic noise does is when you're actually executing, like when you're actually getting the chain of thought, which you then feed into the LLM, you like inject some noise there in the generation process. So like maybe at a step where I'm adding two numbers, I flip one of the digits that I'm adding, producing the wrong answer. And then that, impacts all your calculations downstream. So like suddenly dynamic noise has a much larger, less localized impact on the entire solution versus static noise.
The distinction basically kind of where in the chain of thought it's like static is like towards the end and dynamic is towards the beginning, or
let's say I ask you to solve a problem for me, like generate some training data. I take that, but maybe like somehow there's some noise in that. So like, when you're communicating it to me, I like maybe accidentally flip a digit or like I accidentally miss a line. So like I'm not changing any of the global structure of your solution. I'm just like changing very like local things. That's static noise. Whereas dynamic noise, you make a mistake when you're generating the solution, and then that impacts the rest of the answer. So like now the mistake that you've made has like, messes up step two messes up step three, all the way down the line.
But is dynamic noise really noise in the training data?
It could be, yeah. Like it could be that, GPT-2 tries to solve a problem and it starts from a pretty good place, but then it totally veers off. Like it actually just like does something totally unreasonable. That would be a form of dynamic noise. For like a practical form of static noise would be like maybe GPT-2 knows or GPT-4 knows like the high level steps for how to get to solution. So it does roughly the right things. But when you look at a particular step, it makes a mistake, which doesn't really matter, but like technically speaking is wrong. That would be a form of static noise. One of the main findings of this paper was when you have this static noise. So like, let's say you have some data set which has some level of static noise. Let's say that in every single training sample, you have some noise, okay? So like we investigated different regimes, like in some regimes, only 50% of the training data set had noise. But in this regime, I'm telling you, every single sample is infected. So that's already pretty bad if every single sample has noise, right? And now I'm also telling you, okay, consider the case where 70% of all your digits in your data set are like wrong or flipped or something. Like you've corrupted 70% of the digits in your training data set. So now in every single sample, 70% of numbers are just wrong. Okay. So now fine tune your model on that. How do you expect it to do?
I would think that it would do okay.
You think so? Okay. Well, you're right. So if you add noise to every single training sample and you like corrupt 70% of the digits, it does fine. It gets 100% accuracy, which to me was pretty shocking that you can add that much noise and like have it be fine. The situation breaks down. So if you add noise to 90% of the digits in every single training sample, then you start to get in trouble and like your model just can't learn anything. But I still think it's like pretty remarkable that transformer models are so robust that you can inject that much noise and still get 100% performance.
It reminds me of like, stupid Facebook posts where like you've got some text, but like there are numbers instead of letters and things are backwards and stuff like that. And like the brain figures that out.
I guess so. Yeah. So like there's some structural thing which it's still able to learn and generalize. I think that was kind of the most, how do I want to put it? Sensational finding in my view.
I am surprised though that there's some threshold or something after which it kind of falls apart. In fact, I could have convinced myself that, more errors are better because it focuses the model on the algorithm and not the role of the numbers. Like, for example, the extreme case of that would just be if you blanked out all of the individual numbers, like you're really focusing it on the algorithm and not the numbers.
I agree. Like you would think that some level of noise induces more generalization. And I think that's true if the level of noise is low enough. But we found that this is also roughly the case if you delete like lines. So like you can delete like something like 30% of all the lines in like each solution, the model still is fine. But if you delete more than 30%, then accuracy starts to go down. Dynamic noise was much more destructive, as you can probably guess. Like if you have even like 10% of like all the samples infected with dynamic noise, then you can't really learn anything. Like you're in real trouble. What I'm most optimistic for is, I think lots of other people have more or less said this, but if you take some LLM and then you combine it with some exterior system that allows it to do like more complicated planning, or like in my case allows it to explore and generate much more diverse types of solutions, I think that's the most interesting thing. So I'm skeptical that you're going to be able to get everything you want just by like using the LLM itself. But when you combine it with these other types of systems, which somehow broaden the type of solutions it's able to discover, I think that's where you're really going to get like, superhuman reasoning performance that people are looking for.
Well, Alex, thanks so much for taking the time to share a bit about what you're working on. Very interesting stuff.
Of course, it was a lot of fun.